This is part 9 in a series of videos in which I am reproducing this ADM-3A main PCB. In the previous video in this series I got as far as fitting the clock generator devices, testing that the clock was being generated as it should be. That was all fine. I had intended to move on to the baud rate generator after that and fit these components, but I've had a slight change of plan. Most of the circuits that we'll be dealing with from now on require the clear signals, or one of the clear signals. There are quite a number of clear signals generated on this board, but most sections need clearing when the board is powered up. So I've decided to fit the components to generate the clear signal before going on to any of the other major blocks. It will make sure that all the ICs are being driven properly. If we just leave the clear inputs floating, we could get some odd behavior which could complicate the testing. So the clear signal is generated by this part of the circuit. So it's based around a 74123, and there are some timing components around here. So the way this works is when the power is applied to the main board, this circuit generates a delay and it holds the clear lines all low for a period of time. It allows the rest of the board to be properly powered up and everything to stabilize before the clears are deasserted. And it also allows some test functions where you can force a reset if you want to. So what I'll do is I'll fit these discrete components, there aren't too many, and then we'll get on and fit the ICs and make sure that the various clear lines are all being generated in the way that they should be. Okay, I fitted all the discrete components around the reset circuit. That's all these components down here. Just a few resistors, capacitors and a diode. So we're now ready to fit D1, which is a 74123. I'll actually be using a 74LS123. It should work just fine. Okay, so D1 is the first IC in row D. So I'll get that fitted. And before we fit the rest of the components, which are just buffers, we'll check to make sure we're getting a proper reset signal out of D1. So that's pin 4, so we'll monitor pin 4, and we should see a delayed pulse or rise the signal when we power up the board. So I'll power the board up now, and as we see, there is indeed a delay. I'll slow it down so we can see it a bit more clearly. Okay, the scope is set, we can power up the board. And as we can see, there's quite a lengthy delay between the power initially rising and then the reset being released, which is exactly what we should be seeing. So what I'll do now is fit the remaining components. One thing to note here, and it's one of the issues in doing the layout for this board, is that these are actually all different devices. So although they're all 74LS04s, this IC is D3, this one's D3, this one is K1, and this one is C13, and this one is D2. So they're kind of spread all around the place. The gate usage on the board is very spread out. Now it makes sense when you look at the things that the individual gates are connected to, but it does make the schematics a little bit difficult to deal with. Okay, so we'll fit D2, that's a 74LS00. Okay, and this is component D2, and again on the board we check the ID and it does say LS00. So we'll get that plugged in. And then the next one is D3, and that's a 74LS04. Okay, and D3 is of course this one. Next we have K1, and again it's a 74LS04. Okay, and K1 is this one. And then lastly we have C13 again and LS04. Okay, so it's row C, IC13, which is this one. Okay, so that's all the components in the reset part of the circuit. So what we'll do now is check the 4 reset outputs. All these components are in, they're all fitted, so all we need to do now is see if we're actually getting the proper clear signals, which again it's just a delayed rise on those signals. So we'll start with D3 pin 10. Which is there. We'll get the scope running, power up the board, and again we see the delay. It might be hard to see on the camera, but what's happening is we're seeing an initial small voltage as the device is powered up, but it's giving a low output, and then after a short delay the output rises. Okay, board back off, and then the next output is clear. That was not clear 1. We're now looking for not clear 2, which is D3 pin 8. So down to D3 pin 8, and we should see something almost identical. Okay, all the clears are now working, and the next thing to do is get the main clock working. Now these are the 2 main clock lines, but if we follow it back through, notice that it's being fed by a line that they've called not ICC80, and that's actually fed from down here, and this in turn is fed through from this divider. So what we have to do is to get in place all the parts required to get this clock line up and running, which means we need to fit these components. They're all ICs, so it's just really a case of working our way through, plugging these in, and then in theory we should be getting the clock line coming out. The only discrete components are the 2 resistors to enable the gates. There's one here and there's another one down here, but these are both part of the same SIL package that I fitted previously. So what I'm going to do now is work my way through, fit any of these components that are not already in. Some are already fitted, and then we'll see if we're getting a clock on the output, and we can go from there and move on to the baud rate generator. Okay, I fitted all the components in this part of the board. There's actually quite a few, because as with the reset circuit, they're dotted around the PCB, so they're kind of fairly spread out. I fitted all the ones that are involved in this chain, and because all these are kind of interdependent and they all feed through to ICC80, which in turn feeds through to the input of C15, and then that goes through and generates our 2 main clocks. So the output of all of this is effectively here, and if we're getting a signal here, then we know that it's propagating correctly through this. And because the output of this gate is actually used to control these 2 binary counters, we can be fairly certain that if we're getting the clock signals here, then this entire circuit's working. I will check it all off camera to make sure that all the phases are working and they're all connected to what they should be, but it is really just a case here of seeing if we're getting the clock output. If not, what we'll do is we'll work our way back through and try and figure out exactly why this circuit's not working, but hopefully it's all connected up right. So far nothing untoward has happened. The only issue with the board is the same issue that was with the original board, and again a request for feedback here. The original board had a number of jumpers on it. I don't know if you noticed them in the earlier videos, and that's because certain tracks were just missing. Now I've duplicated that, so the jumpers do need fitting. I've fitted the 2 so far. There's about another 3 or 4 that need to go on the board. and that's to make this board authentic, and also I didn't want to be chasing things that weren't real issues. Two that I know about prevented the proper reset circuits operation. It stopped all the or stopped one of the resets working. Fitted the jumpers, but what's the general thinking? Is it better to correct the board and have it less authentic, or are you happy to fit the links in the same way that the original board was configured? I'd appreciate some feedback on that. I generally go with originality, and then the builders can fit the links. But if you think it might be better to correct the board, then please let me know either way. Okay, so that said, let's get this powered up. I'm going to increase the current limit on the bench supply. We've got quite a few ICs fitted now. Just a quick count up. Okay, so we've got 14 ICs on the board at the moment. It's about a tenth of them. But let's get this powered up, see what happens. We'll monitor the output of C13 pin 2 when I power it up, just in case anything's not there. I'll turn it off straight away, and I'll keep an eye on the current draw as well to make sure that doesn't go too high. So C13 pin 2, and this should give us our CC80 clock, which should be a series of fairly short duration positive going pulses. So I'll power the board up, and we're drawing 120 milliamps, and as we can see, we are indeed getting the correct clock. Pin 12 of this same IC should give us the exact same, which it does. And pin 3 of K7 should give us exactly the same. That's another buffer down here, and okay, good. So all the clocks are working. Just to give you some idea what comes out of these clocks, because they are all used, and they're used for data control. So if we look at, for example, pin 14 of ICD15, we can see that we're getting a clock here, and it's part of a binary counter. So if we go through the individual bits, I'll go down one, and each of these should be a divide by 2. And the last one. And as you can see, they are indeed all doing exactly what we would expect them to. So I'll go through the rest of the circuit, make sure that's working, and then what we'll do is we'll move on to the baud rate generator, which uses the clocks coming out of C14. Let's have a quick look at the circuit for that. Very simple circuit. It's just a series of binary counters set up as a string divider. This switch is not actually fitted. Now, I have included all the footprints for all the possible options that were included, so if you did intend to build one of these and you wanted to fit the options, then you can do, and that includes this switch. It's not normally fitted. It's actually there to allow different clock rates for the transmit and receive, and if you want to have separate clock rates, there's a link that you cut on the board, and then you end up with 2 separate clock rates. By default they're tied together, so both clocks are the same, but you can have them at different clock rates if you wanted to do that. So as I said, what I'll do, I'll get the rest of this checked. I'll get these 3 ICs fitted. I won't fit these just yet. I want to just make sure that these are doing what they are meant to do, and then what I can do is go through, fit the dual switches, fit the flip-flops, and then we should have a fully functional baud rate generator. Now that we've got the main clocks working, so that's the DC clocks and the system clocks, and this part of the character position counter is working, we'll come on to the row counter later. The next thing I want to do is get the baud rate generator working. So I fitted all the components for the baud rate generator, or at least all the ones I currently have. This is the baud rate generator, so it's just really a 3-stage binary counter, so 4 bits per stage, and it's just fed with the system clock, or one of the system clocks, and the frequency of the clock is set so that if you keep dividing by 2, you get all the common baud rates. Now of course there's a couple of odd rates if you go through the sequence that you normally see in RS232, at least low down. So 75 is the lowest one, and the next one up is actually 110, and then you go to 150 and 300. Now if you start with 75, imagine if you're dividing this each time, then we're looking at multiples of 2. So 2 times 75 is 150, so that's fine. 2 times 150, 300, 600, 1200, 24, 48, 96, 1900, and 19,200. So that's fine. The problem comes when you have the intermediate values. There are 2 strange values. We have 110 and we have 1800. Now they have to be handled slightly differently. So there's a reload feature in the counter, and the issue we have at the moment is that the reload feature is driven through a 74H01, and that's in position E1. So normally position E1 down here, just turn the other light on, would normally be a 74H01. It's a 74H01 on the old board. And the odd thing with some 74 series devices, I mentioned earlier that with the clock chip, it's up to you as to which one you pick and make sure you fit the right components so the clock works. For some bizarre reason, some 74 series devices, the pinout's not the same for the different variants of the chip, and the 7401 is a good example of that. The pinout for a 74 LSO1 is not the same as the pinout for a 74 H01. You cannot interchange them on the same board. You could interchange them from the design perspective. You'd have to change the pinout, but it won't work if you just unplug one and plug another one in. I currently don't have any H versions of the device, so I'll leave that out for now. But it is just these 2 gates, but I can't substitute it with a 74 LSO1 because the pinout would be wrong. I have checked the switching and that works fine, so we'll just power it up and check the baud rate generator. We'll have a look at these 2 points first just so that we can see the switching. Before we do that, one other point: if you compare this board with the original board that I have, the built one, then what you'll notice is on that board this device is a 74LS00, so that's the 2 input NAND gate rather than the 3 input. But as you can see here, one of these inputs is permanently connected to 5 volts, so it doesn't actually matter. It works as a 7400 gate anyway. That's this device, and again you can't swap it because well, you could, but you'd have to cut one of the pins off the 7400. But on the old board it's a 7400, and on this board it's a 7410. So make sure that if you do build one of these, as much as possible I've stuck to this schematic, and if you're comparing it against an old board you might find this is a 7400, but it works in exactly the same way. So we'll power it up and we'll check these points first to make sure that we can enable these 2 frequencies, and then we'll check the output at this point, which should give us our full range of baud rates. So I'll power it up, and we're now drawing 180 milliamps, so gone up again because obviously I now have more devices fitted. And so the first thing we'll look at are the control points for the 2 odd baud rates. So we'll start with 110. So that's IC K1 pin 6, and this should just change state when we select board 110. You can see I've also fitted the DIL switches and 2 more SIL resistors down here. So we can see that does indeed change state as I change the switch, and the other one is pin 4, and that should change state when we toggle the 1800 baud line, and as we can see, that's working as well. So what we'll do now is look at this point. All the baud rates should work except 110 and 1800 because this device is not fitted, so there's nothing to gate these two clocks through. We'll just have a quick look to see if those clocks are present before we go any further. So E1 pin 5, and we can see that clock is present, so that's this clock, and then clock 5 is E1 pin 10, and again we can see that that clock is indeed present, so that's working fine. So what we'll do now is monitor this point, and we'll start by selecting baud rate 75, and we can see that's fine. 110, as I say, it won't work, it'll just go high all the time because we can't gate the clock through. And then the next one is 150, and these should just double in frequency each time, so 300, 600, 1200, 24, sorry 1800 is the next one, but again that will just sit high because the gates IC is not there. Then 2400, 48, 96, and 19.2. So we can see that the entire set of baud rate frequencies is working exactly as it should, and even the signals controlling the other two and the two clocks that actually generate those, which is for that to work, then this feedback reset has to be working. So what we'll do now is fit ICK2, which is a couple of flip-flops that. So really what this device does is it tidies up the clock so that the duty cycle is more consistent as different frequencies are selected. So I'll get that device fitted and see if that's working. So that's a 74 LS74. So I'll turn the power off, plug this in. Okay, now we want to monitor pin 6 and also pin 8, so these two should be the same frequency clock, but we'll check both to make sure they're both present. And these go to a pin on the UART, or the two clock pins on the UART. So power it up. And the current's now gone up to just over 180 milliamps. So we'll look at pin 6. Select a baud rate. We'll start at the lowest one again. So you can see how that's tidied up the duty cycle of the clock. We'll go to the next rate, which again it won't work, so we'll see just a static value. 150, 300, so this will just keep doubling in frequency. But you can see how the flip-flop has tidied up that clock. Okay, so the first section works. We'll now look at the next. Okay, so that's working fine. So This entire circuit's working. We need to get this gate fitted. As soon as the devices arrive, I'll pop those in and recheck the circuit to make sure those two frequencies are working. But the rest is now working fine, so that's this entire part of the circuit's up and running. The next thing we'll look at is the rest of the character generator clock circuits, but I will do that in the next video. So it's very similar to the baud rate generator. It's just a series of binary counters, and it just has some gates here to pick out certain values as the counter progresses, and it's fed directly from one of the system clocks that we've generated. Okay, so we'll look at that in the next video. It's coming on quite well. It's no real faults found yet that weren't present on the original, so it's looking quite promising so far, but there is a long way to go yet. As you can see, we have I think we've got 17 devices fitted, and there's about another 135 to go in there, so still a lot to go yet. But everything's looking fine. Obviously we're not really getting anything warm yet. There's only a small fraction of the amount of power that it will draw. And we'll keep an eye on the power, so by the time we've got the board fully loaded, we'll know exactly how much power each of the 3 rails should be providing. Any comments, then please let me know. If there's anything I haven't covered that you want me to, then again please leave a comment.